Hey folks, in this screencast, we'll continue with generalized angular momentum, but now we're going to develop its most useful form, which typically means that we're going to take the expression itself and take the time derivative, and then combine this with Newton's second law, and then this gives us a kinetic expression that we can use to develop equations of motion. So let's start in on this time derivative by applying the product rule to the right side of this expression. So all we've done here is we've distributed our time derivative to each of these terms. So to the first term in the first expression, the time derivative of the position of p with respect to q, and kept our cross product of the mass with the velocity of p with respect to q. And then in the second expression, kept our position of p with respect to q, and then distributed the time derivative into the second term so that we get the mass multiplied times the time derivative of the velocity of p with respect to q. So now that we have this exploded form, let's write it out again, but let's execute these time derivatives of the position vector and then of the velocity vector. So we have the time derivative of our angular momentum of p with respect to q is equal to, and when we take the time derivative here, we get the velocity of p with respect to q as observed in the inertial reference frame. Keep the cross product, so cross the mass of p multiplied times the velocity of p with respect to q as observed in the inertial reference frame. Continuing to the second term, we keep our position of p with respect to q, cross with our mass, and now the time derivative of the velocity of p with respect to q gives us the acceleration of p with respect to q as observed in the inertial reference frame. Now remember, when we do these derivations, we're looking for terms to drop out or simplifications to occur. So the first thing you should see is that we have the velocity of p with respect to q crossed with the velocity of p with respect to q. And so any vector crossed with itself is equal to 0. So now moving to the second term, let's see how we can simplify this. Now we've already alluded to the fact that we want to incorporate Newton's second law into this expression. So let's write Newton's second law. It's all the forces on particle p are equal to the mass of particle p times the acceleration of p with respect to O as observed in the inertial reference frame. But now recall what's critical in Newton's second law is that the acceleration of the point p has to be an inertial acceleration, meaning that it has to be observed in the inertial reference frame and relative to an inertially fixed point. Our acceleration that we have in our expression so far is p with respect to q, and so we can write the acceleration of p with respect to q in terms of the acceleration of p with respect to O, using its vector triad. So now to get this expression, we've taken our relative acceleration and inserted into our time derivative expression. Let's expand this one last term so we get the time derivative of the generalized angular momentum is equal to the position of p with respect to q crossed with the mass of our particle p multiplied times the acceleration of p with respect to O as observed in the inertial reference frame. And then we're going to subtract the position of p with respect to q cross with the mass of p multiplied times the acceleration of q with respect to O as observed in the inertial reference frame. So now we're finally to a spot where you should recognize Newton's second law, or at least a place that we can insert Newton's second law, which is right here. Our mass times our acceleration of point P as observed in the inertial reference frame with respect to point O is the same as the net force applied to our particle P. That means that this first expression is r of p with respect to q cross with all the forces applied to p, and anytime that we have an r cross f, this is a moment. And we call this the moment of p with respect to q due to all the forces that are applied to point p. And so in our final expression, we have that the time derivative of the angular momentum of p with respect to q as observed in the inertial reference frame. And remember, there's no restrictions at all on this angular momentum term. Q can be moving, it doesn't have to be fixed, is equal to the moment of p with respect to q. This is the moment about q due to all the forces applied to point P, And then we have this extra term here, which we're subtracting the position vector of p with respect to q crossed with the mass times the acceleration, and this is of point q, as observed in the inertial reference frame. And so let's take a look at this left-hand side, and let's ignore this right part just for a moment. And you'll see that this looks a lot like our moment of momentum expression, in which we have the time derivative of angular momentum is equal to a moment. Now, whenever the point Q that we're taking this expression with respect to is accelerating, we now have to apply this term. It's a corrective factor, and it has a name. We call it an inertial moment. In other texts, it'll be called a kinetic moment. And so now with this generalized angular momentum form of Newton's second law, we have the most generic form in which we can calculate equations of motion, and we've relaxed any constraints that we've previously placed on point Q. And this is the point on which we've based our angular momentum calculations. Previously in the past, we've used an inertially fixed point. Now Q can be anything that you'd like for it to be. And you'll still get the right answer. So from here on out, whenever you need to use the angular momentum form of Newton's second law, I highly recommend that you just write down this form to begin with. And if the inertial moment isn't necessary, you'll find that out quickly, and that'll be an easy step to apply.